All right. So previously we covered the spatial kinematics, and we studied the rotation metrics, the R. Then we find out that if you will take an R with a dot and multiply with the inverse, you will get angle velocity in skew-symmetric form. And it depends on the way how you do the multiplication, in what kind of frame do you express the motion. It's like if I put the following, actually, let me just AB, since I already put inverse, so it will be like this. So we can do the same motion. We can express in the body frame B, and we have a mnemonic rule that we need to put this symbol of the frame on the main diagonal and put another symbol right here, and we need to put a dot here. So it's like R inverse times R dot, and it also equal to the R transpose R dot. All right. So also we covered the homogeneous transformation matrix, which is the combination of rotation matrix, vector, position vector, and just row of zeros and 1. The same idea goes for the H, but it calls like a twist. So it will be look like this. So here A, B, where should I put a dot? On the left? Okay. The same is true for the B's. In this case, we need to switch places. And also we found out that actually it is an ordinary differential equation that can be solved using an exponential. So from here we can say that the x dot AB equal to twist AB times HAB, just inverse of that, and that one can be solved as an ordinary differential equation, and the solution will be that H equal to the exponent in power of twist multiply the initial configuration. So did we finish the entire kinematics chapter, right? Okay. So when we covered bond graphs, my point was that it is possible to do the multidynamics using bond graphs, but here we have used just one-dimensional bonds, and with each bond we had just expression for the flow and effort, and those were just scalars. But actually we can do this with the multi-bonds, where with each bond we have not scalars but vectors for the flows and efforts, and twist is nothing else as a flow for multidynamics motion, the way of simulation. And the effort will be a range, such as if you multiply twist with the range, you will get power. And it's like a the proper way to do the multi-body dynamics if you want to do, for example, a simulator from scratch, your own. So we covered the rotation matrices, as I already told you, and the rotation matrices are the groups. We covered the homogeneous transformation matrices, all about this stuff about angular velocities and twists. Found out that we can find the rotation matrices and homogeneous matrices by solving the ordinary differential equation. We have a nice Rodriguez formula to do the calculation of rotation matrices, and analogous thing for the homogeneous transformation matrix. Broca's exponential formula to do the direct kinematics. And finally, here just the whole conclusion for the kinematics, such as if we have two frames, we can go from one to another using homogeneous transformation matrices. If we have twist, we also can go from one to another one using adjoint. And if we need to tackle a range, we need to use a transpose adjoint. Did we cover the Jacobian? Okay. Okay. Okay, great.